In this lecture, we'll be looking at the method used in creating the 3D models, which is used in photogrammetry. If you recall in earlier lectures, the intent in photogrammetry is to take aerial photograph and create those 3D models. From it, the 3D models we can extract or digitize the features that we see in the models. Now please note that 3D models are more commonly known in photogrammetry is the term called stereo models. Other books refer to them as neat models. So note that they're all actually referring to the same aspect in photogrammetry in terms of when we create our 3D models. This is our table of contents, and it is very explicit in terms of what is the 3 steps followed in the creation of your stereo models. The first step is in orientation. It involves setting up each photograph in the manner in which it was initially captured. It has to be oriented exactly the same position it was taken out at the time of photography. The next step is relative orientation, where we would remove some of the obvious changes in the X and Y direction for the given objects that you see in the 3D model. So we call that X and Y parallax. You would select 6 distinct points in the 60% overlap area, and then remove the X and Y parallax. And the third step is your absolute orientation, and this is the step where we actually introduce ground control, and the ground control detail that you would get when you go out in the field using your GPS, or if you get very accurate ground control data for your photo control points from the surveyors, that is just as good as more accurate and better to use. So the 3 steps, and know that you cannot start with relative orientation and then do inner orientation. It's a distinct step-by-step procedure. So you first have to do inner orientation, then relative orientation, then absolute orientation. Let's look at each one of these individually. Before we could go into more details in the 3 steps of orientation, I felt the need to explain what is meant by orientation. And orientation, it is the method upon which each aerial photograph, is oriented with respect to the X, Y, and Z axes. In order to create our stereo model, we need to make sure that each photograph is at its exact location with respect to those 3 axes. Now our stereo model is a smaller version in terms of the scale of the model than that of the real world, and this is done typically by doing the orientation steps. Now the traditional method in creating our stereo model is what we use called an equipment. It's an equipment called a stereo plotter, and this stereo plotter it's a large equipment, probably the size of a standard size bedroom, where you would have this equipment connected to a plotter, and the equipment has built into it trays upon which each diapositive placed, and there's a lamp shining light through the diapositive. The optics are used to collect the light rays and focus it into an eyepiece upon which the operator can see the 3D model. Now the whole aspect of setting the each photograph in a tray of the stereo plotter is called in orientation, together with the input of the focal length in the stereo plotter. Now all of that procedure is now automated in a computer environment, which will be explained later on. And this slide, I needed to present to you some information regarding the projection system adopted in the traditional stereo plotters. Now, the traditional stereo plotters makes use of light rays, and those light rays is typical of what occurred at the time the photographs were taken out. The projection system follows or makes use of the lens formula, distance, the focal length, and the distance between your object and the distance between your image, as shown here. So the lens formula is actually built into the projection system. Intersection must occur within the depth of the field of the projection lens. So the basic physics of the projection system is adopting the lens formula. Now, some details regarding in orientation. As I said before at the beginning of this lecture, in orientation, it's also called interior orientation. In orientation, it's the first step you would undertake in establishing the stereo model. And the purpose of the inner orientation is to recreate the geometry of the rays at the time the aerial photograph was exposed or taken out. The procedure here, what we're going to describe in terms of the steps we're going to follow, it's with reference to our traditional analog stereo plotters, and this is by extension applied to the soft copy workstation, which follows the same procedure like our analog stereo plotters. So what is involved in orientation? It involves two things. Firstly, for each of the two photographs used in the creation of a stereo model, the fiducial marks need to be identified in the stereo plotters. And how are they identified? Because the photographs are actually on diapositive and using a magnifying eyepiece, they were able to match up the fiducial marks on the aerial photograph with the plate that it was on the stereo plotter, making sure that the two of them matches up very well. And then the second step in orientation, it involves introducing or turning the dials on the stereo plotter such that the correct focal length of the aerial camera is actually programmed or dialed into the instrument. The second step in creating your stereo model is called relative orientation, and the purpose here is to recreate the stereo model terrain at a smaller scale such that the parallax at 6 points within the 60% overlap is minimized. And in the diagram here, you see photograph 1 overlapping photograph 2 and 6 points were chosen. Those points does not necessarily have to be this control points, but 6 distinct points that can be seen in a photograph and its conjugate. And then the X and Y parallax is removed at that point. Then take it to the second point, the X and Y parallax is removed, digitize it. Third point, X and Y parallax removed. Fourth, same until you reach a sixth point. Now, this procedure actually establishes a plane between each photograph. So you have a plane defined by the perspective center of the camera of the first photograph and the perspective center of the lens of the second of the lens of the camera of the second photograph, and a specific point on the ground. All three of those points together with the point that is related to each photograph, which is on the ground, but it is represented by photograph 1 and photograph 2. All of those points are we have altogether 5 points. All of those 5 points are actually on a plane, which we call an epipolar plane. So as we go from 1.1 to 6, we will be defining 6 epipolar plane, and that is the main intent of this procedure is to minimize the X and Y parallax. The time it takes to do in orientation can take 5 to 10 minutes. Now for relative orientation, using the traditional stereo plotter, it can take 1 to 6 hours depending upon the level of experience. In the soft copy workstation, that time has been reduced drastically because the computer typically would do a lot of the work. However, the traditional stereo plotters, a lot of the work had to be done manually, and because of that, it took 1 to 6 hours. Now, once the orientation is done, the image processing method in the computer using the soft copy workstation, what it does, it compares pixel groupings, and using pixel groupings, you from the left and the right of the photograph is able to determine, within a pixel or two, or root mean square error, a good match. Now, this image selection method in the soft copy workstation, which is the computer application, it does this in about, depending upon the level of experience, you could actually perform relative orientation in less than an hour, and the system actually is much faster. In the traditional stereo plotters, and also by extension the soft copy workstation which we use nowadays, each one of these, using the traditional stereo plotters, there were a total of 6 movements for each projector. So for a given model, one projector would have 6 movements, and the other projector will have another 6 movements. So altogether for one model you have 12 movements, and it involves, for each projector, you can move the projectors in the X direction, Y direction, or in the Z direction, and also there were rotations. Rotation about the X direction. So you have, this is my X-axis here, a rotation in the positive or in the negative direction. It's called omega. A rotation about the Y-axis, identified here, is called, it can be positive or negative, it's called phi. And a rotation about the Z-axis is called kappa. And these terminologies, kappa, phi, omega, is still being used even in the soft copy workstations. The software that is used, rotations around the around the X, Y, and Z are also continued to be called kappa, phi, omega. Now, how do we relate the kappa, phi, omega to the orientation of the aircraft at the time it was taken out? At the time the photograph was taken out, kappa is, as I said before, it's the rotation about the z-axis. Phi is the rotation around the y-axis, and x and omega is the rotation around the x-axis. Now, as I said before, it can be in positive or in the negative direction for each one of those. Now, at the time the photograph was taken out, we need to exactly orient each photograph in terms of its rotation about about the three axes, which is the X, Y, and Z. And we use kappa, phi, omega rotations to orient it, because as the aircraft is flying, the study area is very unlikely that it's going to be 100% parallel to the terrain. So the aircraft is flying along this particular direction and it's capturing photograph. It's actually going to have a bit of a wobble. The pilot has a certain leeway upon which he's going to try to get it as much as possible close to what is required on the project specification. But he has to deal with changes in the direction of the wind and also the speed of the aircraft. All of that is affecting the direction which the aircraft is flying. So as the aircraft is flying, we need to make sure that we capture or determine what is those rotation, kappa, phi, omega. Using the analog stereophoto, as I said before, it can take between 1 to 6 hours long ago. It involves iterative process. And what I try to do here is summarize the iteration regarding the 6 points. And it's just FYI, just to give you an idea of what was done in order to remove the parallax at the relative orientation stage. At point 1, remember before I said there was 6 points that were selected within the 60% overlap area of a photograph and its conjugate photograph. Well, at point 1, what they had to do was do a swing of look at point 1 and swing projector 2. Try to get point 1 to match up with point 1 in the first photograph and point 1 and in its conjugate, second photograph. At point 2, then it'll go to point 2. By the swing of projector 1, they would remove the parallax. Now, once you do that, it would send the parallax at point 1 off a bit. So they had to repeat step 1 and step 2 until points 1 and 2 are free of parallax. Now, once they remove the parallax at step 1 and step 2, then they will go to point number 6, tip the projector 1, and by tipping projector 1, they would match up point 6 between the two photographs, a photograph and its conjugate. Then they would have gone to point number 4 by tilting the projector. So tip and tilt is actually, and swing is actually terminologies and rotation and knobs that they will have on the stereophotos. So at point number 4, would tilt projector 1 and over tilt it. So this is an overcorrection, and that overcorrection usually was 3 times the amount of tilt required to remove the parallax. Now once they do that at point number 4, they had to go back and check point 1, 2, 4, and 6 and make sure that they are in line. So this is where it actually took a lot of time. And if you're not an expert with a lot of experience, then this would have taken the full 6 hours. And then once they remove those parallax at point 1, 2, 4, and 6, then they would move to point number 5. Point number 5, then they will tip projector 2, check for the parallax at point 3, and repeat all of the movement until the parallax is removed from all 6 points. So by tipping projector 2 at point 5, it would have moved off the other points after you did the first iteration, and they had to go and check them again. So it was, as you can see here, a long and drawn out process. Now to the expert in using the stereo plotter, this would have taken them at most 1 hour. On this slide, I just wanted to reiterate the different number of motions or movements that a stereo pair has. And as I said before, stereo pair consists of a photograph and its conjugate, which is its neighboring photograph. Altogether, so a pair photograph would have 12 motions. So that is, each photograph has a X, Y, and Z motion, and also a kappa, phi, omega. Relative orientation on analog stereo plotter usually require 15 to 60 minutes. That is for if you have a lot of experience, but it can range from 1 hour to 6 hours, and depending upon the experience of the operator. Until setting up the stereo model, it's called absolute orientation, and this is the step where we introduce the ground control that was collected by GPS surveys or from licensed land surveyors who went out to get the coordinates of the photo control points that would have been captured or would have been captured at the time of the photograph was taken out, and using the photo control points, the X, Y, and Z values, and also defining the coordinate system, a scale would be set for the model. After relative orientation and inner orientation, the stereo model is geometrically similar, but a smaller version of the model will be created when we start to introduce the ground control, and also by using the height information, we call that leveling. We would be creating a stereo model, a smaller scale stereo model of the area being observed. Now, in the traditional stereo plotters, how was the absolute orientation done? This was done making sure that the relative orientation does not go out of sync, because it took a long time to achieve that. But what they did was actually change the distance between two projectors. So between projector 1 and projector 2, they were able to change, make it smaller or larger, and then they would, to introduce the height information, they would tilt the projectors together. So the entire stereo plotters, the two projectors, would have been tilted using special knobs, of course, that would have achieved these objectives. Now, using the soft copy workstation, this is easily done. Once you define the coordinate system and you put in the ground coordinates for the photo control points, You identify where those points are on the model. The system does a least squares adjustment and creates a stereo model that is very easily interpreted and easily used to make measurements. To summarize, what was done using the analog stereo plotters, in order to achieve that, after they did the relative orientation, they had to first of all collect the X, Y, and Z values of the photo control points. They typically during that time would have required a minimum of 3 control points. Alright, but it's recommended that you collect, I would say, probably 4 or even 6 control points. The required corrective rotation is resolved in 2 components. So, as I said before, they were able to increase the distance or decrease the distance between the projectors together at the same time, and then by leveling the projectors at the same time, increasing the height, decreasing the height, they were able to introduce the height component into the model. Now once they get the 3 control points, at least 3 control points, they were able to use the analog stereo plotter to introduce the ground control into the model. And this was done together with a grid that they would have plotted manually on a piece of paper to scale, plotted the ground control points on that paper, and then move the point on the model, move the floating mark, which is your measuring point on the model, to the first ground control point, and then on the plotting table relate that first control point to where it is on the plotted grid. And they do the same thing for the other control points, and that way they were able to scale down the model of the stereo model to the desired model that they want to plot to fit that particular grid. This took on average between 2 to 3 hours, making sure, and again this was an iterative process, being careful not to disturb the relative orientation. In the analog stereo plotters, the time, this time 2 to 3 hours, can be shorter, of course. If you have more experience, this can be done in less than 2 hours. In your soft copy workstation, which is your computer driven program that does this, you just put in the X, Y, and Z values, define the coordinate system, identify where these ground controls are on your stereo model, and the system does least squares adjustment and creates a model for you, and this can take I would say 15 minutes. Great improvement. This is an example of a stereo model that was created using computer software. As you can see here, we have, if you look at the 2 images together, it looks a bit blurred. That is because one image is displayed in red and the other images is displayed in blue. When overlaid and using a special anaglyph glasses or spectacles, viewing the 60% overlap, you could actually see that this area here is actually a mountain, and in between 2 mountains we have a water tank. And if you could get a pair of anaglyph glasses, which is relatively cheap, they are the types that have paper material. You might want to get one just to look at the this stereo model. Is very useful. And What you see here on your right, it's actually a view of the same area on my first photograph and its conjugate, the view and two photographs the same area. On your left, you see different point, line, and polygon features being used to digitize based upon the features what you're trying to capture. Digitize the features. When you digitize, you are typically collecting CAD data which can be read by AutoCAD, and you can export that into AutoCAD or even MicroStation. So this is, after you do the 3 steps of inner orientation, relative orientation, and absolute orientation, you know how a scaled down version of the model of the area of interest. Now once you have the stereo model, you can picture this, look at this figure here where you can measure off the heights of different points on the terrain, or even if there's a building located here, I can measure the top of that building, etc. So this is an ideal scenario where I can use a floating mark, which is the cursor, just like my pointer here. That floating mark actually makes wherever you put it is actually giving you a height at that point. Okay, so at your fingertips in a smaller model of the area of interest, you have the ability to capture whatever information that you can see there in the model. In order to make the height measurements, as you can see here in this little diagram, the height measurements are actually made using what we call, as I said before, a floating mark. This is the previous diagram. Let's look at it at a cross section. If this is my terrain here, a cross section of it, and these locations here are actually my floating mark, where I, just like my mouse, I can move it around. I could move my floating mark and put it anywhere on this surface. If I want to get the X, Y, and Z values of it, I'll put it there and read the measurements, remove the parallax. Take it here and read the measurements by removing the parallax. If I want to get the height into the ground, or the X and Y location, I can take it into the ground. If I want to get the height above the terrain, let's say there was a building here, I can put the floating mark on top of that building and measure off what's the height, but that height is going to be the height including the height above mean sea level. So this is a good representation of what are the functionalities of our floating mark. Now, since the beginning of this lecture, we've been talking about creation of stereo models using photograph and its conjugate photograph. Now, remember, when we do a flight plan of an area, it's not just 2 photographs, it's probably at least a few hundred photographs. So the question is, how do we use all of those 100 photographs? Does it mean that we have to create individual models for them? The answer to that question is no. We do not have to create stereo models for each one of them. That's where the whole concept of area or triangulation comes into play. Area triangulations take into consideration all of the photographs for the certain study area, gathers all the ground control that was collected for that study area. It takes into also consideration the focal length and the fiducial marks. All of this data is fed into the computer, and also any tie points between photographs and between runs. All of that is identified in the area triangulation as data input. What it does, it takes all of that information, the coordinate system, and creates or does a least squares adjustment to create the best fit model. And that's what we call exterior orientation. Exterior orientation is the process of gathering enough information about individual images to be able to calculate the ground coordinates of each image center. So we want to find out what is the ground coordinates of all of the perspective centers of the camera at the time of each photograph was taken out. Then using that, this is determined using the ground control data that would have been captured in all of the photographs. All of that is used in our area triangulation. Alright, this concludes our discussion about orientation procedure in photogrammetry. As I said in previous lectures, please download the PowerPoint presentation, the notes page, and go over the PowerPoint presentation. Make sure you understand what's going on, and we will continue with the next lecture.